Now I'm going to discuss about thermodynamic properties of fluids. Some properties like the volume, pressure, temperature. So these properties we can easily measure with the help of some instruments. And other properties like specific volume or the density we can measure. We can measure with the help of with the knowledge of the measurable properties, the volumetric properties, but some properties like energy properties we cannot measure directly, but with the help of some fundamental property relations we can determine those type of properties. So like the internal energy or enthalpy or the Gibbs free energy or Helmholtz energy. So now I'm going to explain about what are the fundamental property relations. So first coming to the general energy terms like internal energy, we know that D internal energy UE du equals to, according to the first law of thermodynamics, d nu equals to dq, the reversible, plus dw, the reversible. So this is the first law of the change internal energy equals to the heat applied and the work done, and dq reversible. The reversible heat is given by the TdS, and the work done, it is given by minus PdV. Now we substitute this one, du equals to TdS minus PdV. So this is for n moles, d of nu equals to T. For 1 mole or n mole, temperature is a constant, and but entropy is changes to dns minus d of nv. So this is one relation for internal energy as a function of temperature and the pressure. And now coming to the second energy term, that is the enthalpy. Enthalpy, we know that H equals to U plus PV, or the differentiation for n moles, this is NH equals to Nu plus PNV. If you differentiate this equation, d of NH equals to d of Nu plus PdNV plus NV dP. And from this fundamentally proper relation, so dNu is given by dDNS minus PdNV. So this is dDNS minus PdNV plus PdNV plus NVdP. So d of NH equals to TdS TdNS plus NVdP. So this is the second relation. And now coming to the Gibbs free energy, that is G. G equals to H minus Ts. For n moles, this is Ng equals to NH minus TNS. So d of Ng is d of NH minus d of NS minus NS dt, and d of NH is ddNS plus NVdP minus ddNS minus NS dt. So ddNS and ddNS get cancelled. So d of Ng equals to NVdP minus NS dt. So this is for the Gibbs free energy. And another energy term is that is the Helmholtz energy, that is given by that is represented with symbol A. A equals to U minus Ts, and Na, for n moles it is Na equals to Nu minus Tns. The differentiation of this equation gives d of Nu minus T d of Ns minus Ns dt. Now d of Nu, from the first property relation, d of Nu is TdNS minus PdNV. Minus TdNS minus ns dt. So TDNS and TDNS. So d of NA equals to minus PDNV minus ns dt. So this is another relation. So generally these four, d of nu and d of nh and d of ng and d of na. So these four relations are called as a fundamental property relation for homogeneous phases at constant composition. Suppose if we are taking n equals to 1, then this equation becomes u equals to TDS minus PDV, DH equals to TDS plus VDP, and DG equals to VDP minus SDT, and DA equals to minus PDV minus SDT. So these are the fundamental property relations which are used to find out the energy properties. And another Maxwell developed some relations, so which are also useful for finding out the thermodynamic properties. So those relations are based on, suppose if Maxwell's relation. Suppose if f is a function of x comma the y, then df equals the total differential, df equals to dou f by dou x into dx plus dou f by dou y into dy. So this is a total differential, and if you take dou f by dou x equals to some p and dou f by dou y equals to some q, then if you differentiate with respect to y, dou y and dou x is equals to dou p by dou y at constant x. Similarly, if you differentiate this with respect dou square f by dou x dou y is equals to dou q by dou x at constant y. So these dou square f by dou y dou x and dou square f by dou y are the same. So therefore, dou p by dou y at x is equals to dou q by dou x at y. So based on these relations, Maxwell developed four relations. So from the fundamental property relations. So first take du equals to TDS minus the PdV. So du equals to TDS minus PdV. So here, so u is a function of s comma v. So du equals to dou u by dou s at constant v into ds minus dou u by dou v at constant s into dv. So now equate this is equation 1 and equation 2. So in this equation T equals to dou u. So because the left LHS side is the same, du and du, and so the coefficients are the same. So T equals to dou u by dou s at V, and similarly P equals to minus P equals to dou u by dou V at S. So now the differentiate the first equation with respect to V. So this is dou square u by dou V and dou S at constant S comma V is equals to dou T by dou V at constant S, and this is differentiate with respect to S is equals to minus dou P by dou S at constant V. By equating these two, finally we will get dou T by dou V at constant S equals to minus dou P by dou S at constant V. So this is one relation. So dou T by dou V at constant S equals to minus dou P by dou S at constant V. Now from the second fundamental property relation, so that is dH equals to TdS plus VdP. So dH equals to TdS plus VdP, and H is a function of S and P. So dH equals to dou H by dou S at constant P into ds plus dou H by dou P at constant S into dP. So this is a total differential, and equating these two equations, dou H by dou S at P equals to H and dou H by dou P at S is equals to V. Now differentiate this equation with respect to P. So dou square H by dou P dou S at constant P comma S is equals to dou H by dou P, sorry, this is T. So dou T by dou P at constant S, and this is dou square H by dou S dou P at constant S comma P is equals to dou V by dou S at constant P. So these two are same, so the dou T by dou P at constant S equals to dou V by dou S at constant P. So this is the second relation. Dou T by dou P at constant S is equals to dou V by dou S at constant the P. Similarly, for Gibbs free energy, dG equals to VdP minus SdT. VdP minus SdT, and G is a function of P comma T. So dG equals to dou G by dou P at constant T into dP plus dou G by dou T at constant P into dt. By equating these two, 1 and 2, V is equals to dou G by dou P at constant T and minus S is equals to dou G by dou T at constant P. If we differentiate with respect to T, dou V by dou T is equals to dou square G by dou T dou P at constant T comma P. And similarly, differentiating with respect to pressure, so dou S by dou P at constant, the temperature is equals to dou square G by dou P dou T at constant P and T. So now equating these two, we get another relation, that is dou V by dou T at P equals to minus dou S by dou P at T. So this is another relation. So dou V by dou T at P is equals to minus dou S by dou P at T. So similarly for Helmholtz energy, so dA equals to minus PdV minus SdT. So A is a function of V and T. So dA equals to dou A by dou V at constant T into dV plus dou A by dou T at constant V into the dt. So by equating this equation and this equation, P is equals to dou A by dou V at constant T minus P, and minus S is equals to dou A by dou T at constant V. So now the differentiate with respect to temperature. So minus dou P by dou T at constant V is equals to dou square A by dou T dou V at constant T comma V. So similarly, this is differentiate with respect to volume, dou S by dou V at constant temperature. This is dou square A by dou V dou T at constant T and V. So now equating these two, finally we will get dou P by dou T is equals to dou S by dou V constant with constant T. So this is the final relation, dou P by dou T is V equals to dou S by dou V at T. So with the help of these fundamental property relations and the Maxwell relation, we can find any thermodynamic properties.